Hey everybody. Today's short lesson we're going to talk about simple machines and efficiency and mechanical advantage. And we're going to look at this through this simple example of an inclined plane. So let's say that we have a box over here, a 5 kilogram box, and we need to move it from position A to position B. So we could just lift it directly, but if we want to make things a little easier for ourselves, we can use an inclined plane, a simple machine, and push the box up this inclined plane. The inclined plane in our example here has dimensions, horizontal length of 5.0 meters, vertical length of 2.0 meters, and then the diagonal length here is 5.4 meters. So the first thing that we have to understand with any simple machine, including an inclined plane, is that the law of conservation of energy must be followed. In other words, the input work that we do must be equal to the output work done on the object. So in this particular example, the output work is going to be the change in gravitational potential energy for our 5.0 kilogram box. The input work is going to be the amount of energy that we use in moving the box from position A to position B. And if we substitute in what we know for work, the equation for work is force times distance, we get force input times distance input is equal to force output times distance output. And if we rearrange that a little bit, we get the ratio of output force to input force is equal to the ratio of input distance to output distance. So what this ratio tells us is that it is possible for us to exert a different input force than the weight of the box and still do the same amount of work for an ideal machine such that we don't violate the law of conservation of energy. The catch is if you have a lower input force, you will need to have a larger input distance in order to keep the ratios in this equation equivalent. So you might be pushing with less force, but you have to push through a greater distance. So let's take a look at how exactly the inclined plane here helps us with our task of moving our 5 kilogram box from position A to position B. So the inclined plane, like all simple machines, has the ability to multiply forces. The amount of multiplication that you get for a particular simple machine is quantified by that machine's mechanical advantage. So let's assume ideal conditions here to start out. Let's assume there's no friction on this inclined plane. In that instance, the mechanical advantage of the inclined plane could be found by either looking at the ratio of the output force to the input force or the input distance to the output distance. And you'll notice that this is the exact same ratio that we had on the previous slide derived from the law of conservation of energy, and that is not coincidence. That is the way that it should be if we're thinking about it from energy conservation perspective. So for this inclined plane, we know the distances, we know the dimensions. Let's talk about what the input distance and the output distance would be in this case. The input distance is literally the distance through which we must push the box, which is going to be the hypotenuse of the incline. And then the output distance is the change in height, which would be 2.0 meters for this particular inclined plane. So if we set up the ratio, we have an output distance of 2.0 meters, that goes in the denominator, and an input distance of 5.4 meters, that goes in the numerator. And we do see here that the dimensions cancel, so meters and meters will drop out. This mechanical advantage ratio is dimensionless. We get 2.7 for our mechanical advantage. So think about this conceptually. What that's saying is this inclined plane will multiply your input force by 2.7. So if you're trying to, in this case, move a 5.0 kilogram box, which would have a weight of 50 newtons, you're not going to have to push with 50 newtons of force. Instead, you'll have to push with 50 divided by 2.7 newtons of force, because your input force will be multiplied by that mechanical advantage of 2.7. You can also find the mechanical advantage if you know the input and output forces, the ratio of output force to input force. More frequently, this ratio of output force to input force is going to allow us to solve for our pushing force. What would be the applied force required to move an object with this particular incline? So let's write that down up here. The mechanical advantage we calculated from the distance is 2.7 for this inclined plane. And let's give ourselves a little bit of room to work here. Take a look at how that might be helpful. So let's say we have this inclined plane. We know its mechanical advantage is 2.7 from its dimensions. I want to know for a 5.0 kilogram box, what force will I need to push up the incline in order to move this box from position A to position B. So I take the ratio of output force to input force, which is equal to the mechanical advantage, and I solve for input force, because that's what I want to know. How much force am I going to have to exert? So the input force is going to be equal to the output force divided by the mechanical advantage. So the question then becomes, what is the output force? Well, the output force would be the weight of the box, just mg. So the input force is going to be mg over 2.7, or 50 newtons over 2.7. And again, this was the input force. And that is going to work out to be like 18.5, I believe, newtons. So we do see that if this is an ideal inclined plane, we end up pushing with quite a lot less force than the actual weight of the box, 18.5 newtons. We do have to push through a greater distance than we would if we had just lifted the box directly in the vertical direction. But that's because we can't violate the law of conservation of energy. If you're going to use less force, you'll have to exert that force through a greater distance in order to do an equivalent amount of work. Okay, we're going to break there. In our next video, we will take a look at efficiency.